Hi, we're going to discuss how to conceptualize the delivery, filtration, and excretion of solute X using our knowledge of renal abbreviations to quantify these different processes. So let's start with rate of solute delivery to the kidney. So we're talking about an amount of solute X delivered to the kidney per unit time. So remember, an amount is a concentration times a volume. And we're talking about a flow rate, so it'll be volume per unit time. So number one, what we would do is we would go over here and we would write the plasma concentration of X times the flow rate, which is going to be the renal plasma flow. Okay, so that product is going to be the amount of solute X being delivered to the kidney. So over here we can write plasma concentration of X times the renal plasma flow. Okay, good. Next, let's talk about the rate of filtration of solute X. So we go over here and we go, well, this is the afferent arteriole. We have the glomerular capillaries where our filtration occurs. And we know that we're going to have this solute get across. That process is called filtration. And assuming in this case that none of the solute X is bound to plasma protein, it's 100% free to cross, we would then be considering the concentration of X in the plasma, which should be the same that we had over there. Now, if it was bound to protein, it was a fraction of it was bound and a fraction was unbound, we'd have to multiply by the free concentration. So we'd have to multiply by the fraction unbound. But in this case, we're going to just leave it as px for now. And then we would multiply by the flow rate. In this case, the volume that's coming across here per unit time is going to be the glomerular filtration rate, which is GFR. And so this would be number 2. Okay, and over here we have Px times the GFR. All right, so that would be how we would represent the volume of plasma crossing per time times the plasma concentration, and collectively that would be the amount of X getting across the glomerular capillaries into Bowman's space. That's right there, this first part of the kidney. Now, we're summarizing the nephron here. We're just drawing a straight tube. We're not going into different nephron segments. And we have the urine over here as the output. So now we want to talk about, well, how would you quantify the excretion of X per unit time? So that would be number 3 over here. And we need, again, a concentration. But in this case, we're talking about the urine. So we would be dealing with the urine concentration of X. And then the flow rate in this case would be V dot, the urinary flow rate. Now remember, the V dot is a much lower number than the GFR. Remember, you're reabsorbing a lot of water, over 99% of the water in most cases, and this is a very small volume in comparison to the GFR. And nevertheless, we still have a volume, and we have to multiply that volume times the concentration to get an amount. And so that would be the V dot. Okay, and so over here, this would be Ux times V dot. Now that we've put together some of these major delivery of X to the kidney, filtration, and excretion, we could also add a little bit more in between, and we know that for X, it's possible that X could be transported, right? So we know that it's possible that X could be reabsorbed, okay? It's possible that X could be secreted, okay? And together that would be, you wanted to call it transport of X, that would be fine. Now, not all substances behave this way. Some substances are not reabsorbed or secreted, things like inulin, for example. You have substances that are only reabsorbed, you have substances that are only secreted, and you have substances in some cases that are both reabsorbed and secreted. So if we wanted to just write out, keep the bookkeeping here, we would say, well, the Ux V dot, that's the amount of substance X that's exiting the kidney, that has to be equal to what came in. So that would be Px GFR. Then you'd have to take into account anything that you'd be subtracting through reabsorption or adding through secretion. Now, in the case of something that's not reabsorbed or secreted, this part would go away, Rx and Sx, and you just have Ux V dot equals Px GFR. Or if you had something that was just secreted, the reabsorption was 0, you would get rid of the reabsorption term. And if it was just reabsorbed and not secreted, you would get rid of the secretion term. So that's a good way to think about it. And in the cases where you have Sx and Rx occurring also for a substance that's doing both, you would be looking at the net secretion of X or the net reabsorption of X. Just overall, what's the overall sum of those two processes?